Here I am sharing the PPT. I am presenting the PPT. Is it visible to all? Okay. So in today's session, we are going to discuss about prime numbers and formats and Euler's theorems. After that, we are going to discuss about Chinese remainder theorem, that is also called as CRT. So prime numbers are used in number theory as well as cryptography. These are the main part in the number theory. And then Fermat's theorem, and then Euler's Totient function. So this Euler's Totient function used in Euler's theorem. After that, we are going to discuss about Chinese remainder theorem. So first, prime numbers. So you already know about prime numbers. Okay. So the definition: an integer p is greater than 1 is a prime number. Okay. So any integer that is greater than 1 said to be as prime number if and only if its only divisors are plus or minus 1 and plus or minus p, then only we can say that that number is a prime number. So the divisors only one and itself, that is called prime number. So tell me some prime numbers. Tell me some prime numbers which you have known. So 1, 3, 5, 7, 11, 13, 17, 19, and so on. So why? Because those numbers have only the factors 1 and itself. So that is prime number. Next, we can write any number. Okay, any integer a is greater than 1 that can be factored in a unique way. So we can write any number by using the prime factorization. So for example, so we take 91. Okay, sorry, 91, that is 91, 91. We can write it as 7 into 13. Okay, so 91 written as 7 into 13. Next, 12. 12 is written as 2 into 2 into 3. So this is also written as 2 square, 2 square into 3. So in this format. Okay, so if a is equals to 12, here p1 power a1 into p2 power a2 into and so on pt power at. So we can written in this format. So here p1 means 2 and a1 also 2. Okay, so p2 is 3 and a2 is 1. Okay, we can written in this format, that is called factorization method. So here p1 p2 and so on p3 are prime numbers. Here p1 is less than p2, p2 is less than p3, and so on. So see, here p1 is less than p2. Okay, so in this way we can return any integer by using the prime factors, and ai is the positive integer. So here a is the positive integer. So this can be represented in another way, represented as this way. So a is equals to product of set of prime numbers. So here prime numbers is in the form of p. p power ap. Okay, so we can return uh, same as same in this format also. Here capital P is a set of all prime numbers. From this capital P we are selecting uh, prime numbers. So set of prime number means 1, sorry, 2, 3, 5, 7, and so on. So this is capital P. From this set, we are choosing again small p. So in this example, we chosen 2 and 3. Okay. So in powers, we are having 2, 1, 3, 4, anything. So the right hand side of the product or all possible prime numbers p for any particular value of a. So for any value, we are having right side prime numbers. Okay, and most of the exponents will be 0. So here uh, so most of the exponents will be 0 means that is 1. Okay, so this is about prime numbers. So we will take another example also. So for example 3600 3600. So to write prime factors for this number, where we can write this as 3600. So 2, then we get 1800, again 2, 900, next again 2, so 450, again 2, 225, next 3, so 3 sevens, 3 fives, next again 3, 3 2, 3 5, next 5, so 5 fives, 25. So we can written as 2 power 4 into 3 square into 5 square. So here P1 is 2, P2 is 3, P3 is 5. So P1 is less than P2, P2 is less than P3. Okay, so we can return any positive number by using the prime factorization method. So next, Fermat's theorem. So there are two important theorems play important roles in public key cryptography. Those are Fermat's theorem and Euler's theorem. So these two are very important in public key cryptography, like either RSA algorithm, Diffie-Hellman key exchange. So in those algorithms, we have to perform large number of powers. We have to calculate the large number of powers, and after calculation of powers, and we need to perform a division and find the remainder. So for performing modular operation for the largest integers, we need to uh, we can solve by using these two theorems. Okay, 1 minute. No, wait 1 minute. Okay. So Fermat's theorem states that if P is a prime and A is a positive integer, not divisible by P. So you know that what is relative prime number. So relative prime number means if two numbers are having only co-primes as one and itself. One is the maximum uh, prime factor for both those numbers. So if P is a prime number and A is a positive integer, not divisible by P. So A is not divisible by P. Okay. So not divisible by P. Then the Fermat's theorem says that A power P minus 1 congruent 1 mod P. So you know the congruent function. So the meaning of this congruence is A power P minus 1, A power P minus 1 mod P mod P is equals to 1 mod P. So this property already you learned in previous session. So here the remainder is 1 and here also the remainder is 1. Okay. So this is the Fermat's theorem. And here A and P. So A is not divisible by P, then only this theorem is true. So take an example for Fermat's theorem. So P. So here 7 is not divisible by P. Okay. So then here the remainder is 7. So if 7 divided by 19, then the remainder is 7. Okay. So here the statement, uh, the theorem statement P is prime. So you see here P is prime, 19 is prime, and A is positive integer. So 7 is positive integer, not divisible by P. So 7 is not divisible by P. Then this theorem is true. So you already know that how to substitute. So A value 7. Okay. So P value 19. 19. So minus 1 congruent 1 mod P. Okay. P value 19. So you know how to calculate 7 power 18. Okay. So how to calculate 7 power 18? So first we are performing 7 mod 19. Okay. So 7 mod 19 value. What is the 7 mod 19 value? Tell the answer. What is the 7 mod 19 value? 7. Okay, so 7 mod 19 means 7. Next, 7 square. So 7 square mod 19. So 7 square mod 19 means 49 mod 19. Mod 19. So 19 2 are 38. So 49 minus 38, 11. So 7 square mod 19 is 11. Next, 7 power 4. So 7 power 4 mod 19 is equals to, so we can write 7 power 4 mod 19 as 7 square mod 19, 7 square mod 19 whole square mod 19. So this is the modular arithmetic property. Okay, so 7 square whole square means 7 power 4. So we know already 7 square mod 19 value as 11. So here 11 square mod 19. So 11 square value 121. So 121 mod 19. So again 11 square 121, 19 6 are 114. So 121 minus 114, 7. Okay. Next 7 power 8. 7 power 8 mod 19 is equals to, so we can written as 7 power 4 mod 19. Okay, 7 power 4 mod 19 whole square means here 4 into 2 8. Okay, into mod 19. Okay, now we know that 7 power 4 mod 19 value 7. So 7 square mod 19. So 7 square value 49. 49 mod 19, again we got 11. And now 7 power 16 mod 19. 7 power 16 mod 19. Now 7 power 8 mod 19 whole square mod 19. So 7 power 8 mod 19 value 11. So 11 square mod 19. So is equals to, so 11 square mod 19 means 7. Okay. Now we need 7 power 18. So 7 power 18 congruent 1 mod 19. So this meaning 7 power 18 mod 19 mod 19 is equals to 1 mod 19. Now, so 7 power 18. So we know this 7 power 18 will be written as 7 power 16 into 7 square. Okay, 7 power 16 into 7 square mod 19. Okay, now by using again modular arithmetic property, we can, this can be written as 7 power 16 mod 19, 7 power 16 mod 19 into 7 square mod 19, 7 square mod 19, whole mod 19, whole mod 19. So this is also one of the modular arithmetic property. So these arithmetic properties are explained in last session by the Anupam sir. Okay. Now we know the 7 power 16 mod 19 value 7 into 7 square mod 19 value 11, 11 mod 19. So 7, 7 into 11, 77. 77 mod 19, answer is 1. Okay. Now here also the answer is 1. So both are same. Okay. So that's why we can take any positive integer a and a prime number p, then we can say that a power p minus 1 congruent 1 mod p. When a is not divisible by p, then only we can say that. Are you understand? అర్థమైందండి ఇది ఫర్మాట్స్ థీరం. సో మనం మాడ్యులర్ అర్థమెటిక్ ప్రాపర్టీస్ ఎలా యూజ్ చేస్తున్నాము అనేది ఇక్కడ ఇంపార్టెంట్. ఓకే. ఓకే. నెక్స్ట్ Fermat's little theorem. So Fermat's little theorem is the alternative approach for Fermat's theorem. Here some small changes are made. Here if p is a prime number and a is a positive integer. Okay. So if p is a prime number, a is a positive integer. So the Fermat's little theorem is a power p congruent a mod p. So previously a power p minus 1, okay, a power p minus 1 congruent 1 mod p. So this is Fermat's theorem. But Fermat's little theorem is a power p congruent a mod p. So the difference between Fermat's theorem and Fermat's little theorem is that a be relative prime to p, but this form does not here. So here a is relative prime to p in Fermat's theorem, but here in Fermat little theorem a is not relative prime, does not require relative prime between a and p. So you know relative prime, the GCD of two numbers is 1. Okay. uh, Example. So if p is equals to 5, a is equals to 3, here both p and a are relative prime numbers. Okay. Here 5, 10, these two are not relative prime, but it both follows Fermat's little theorem. Okay. So this is the example for uh, relative numbers, relative primes. Here a and p are not relatively prime, but both follows Fermat little theorem. So here, so a value is 3. Okay. So p value is 5. So mod 5 is equals to, so a value is 3 mod 5 mod 5. Okay, so this is Fermat's theorem. So 2 power 5, sorry, 3 power 5. So 3 power 5 means, what is the value? 339, 27, 243. 3 into 3, 9 into 3, 27. 27 into 3, 81. 81 into 3, 243. So 3 power 5 means 243 mod 5 mod 5. So the value of 243 mod 5 is 3, remainder 3. Here also 3 mod 5 remainder is 3. So both are same. So uh, it shows that this Fermat's little theorem. And here p value is 5, a value is 10. A value is 10, p value is 5, mod p value is 5 is equals to a value is 10, 10 mod 5 mod 5. So you see that, so 10 power 5 mod 5. So 10 power 5 means 10, 100, 1000, 10,000. 10 power 5. Okay. So 10 power 5 mod 5 result is 0, and 10 mod 5 result is 0. The remainders are same. Okay. So this is Fermat little theorem. Now Euler's theorem. The second one is Euler's theorem. So before going to Euler's theorem, okay, we have to see Euler's totient function. There is a function that is called Euler totient function. So here Euler's totient function is represented as pi of n. So this is represented with pi of n defined as. So what is pi of n? So it can be defined as the number of positive integers less than n and relatively prime to n. Okay, so the number of positive integers less than n and relative prime to n, that is called totient function. So here pi of 1, so here n value is 1, then pi of 1 is equals to 1. And so this is basic statement. Now so these are the uh, n values, and these are the totient values. Okay, so for 1 there is only one relative prime number, that is 1. For 2, okay, the relative prime number is only 1. Okay, for 3 we are having two relative prime numbers, that is 1 and 2. Okay, so 1 and 3 are relative prime, 2 and 3 are relative prime, 3 and 3 no relative prime. Why? Because here the common factors are 1 and 3, so that's why we are not taken 3. For 4, 1 is a relative prime number, 1 and, okay. Next, for 2, 2 is not a relative prime number. So why? Because the GCD of 2 and 4 is 2. Next, 3. So 3 is a relative prime number. Why? Because the GCD of 3 and 4 is 1. Okay, so 1, 3. So that's why the count is 2. Okay, so here pi of n defined as the number of positive integers less than n. So these are the less than n. Okay, and relative prime to n. Okay, these are the relative prime to n. Next, 5. So 1, 2, 3, 4. So these four numbers are relative prime to 5 and less than 5. For 6, so 1 is relative prime for 6, true, and 2 2 is not relative prime. Because why? Because GCD of 2 and 6 is 2. 3 is not relatively prime to 6. Why? Because the GCD of 3 and 6 is 3. Okay. Next 4. 4 is also not 5. 5 is relative prime to 6. Okay. Why? Because GCD of 5 and 6 is 1. So the count of these two is 2. That's why here we pi of n value 2. So pi of 7. So 1, 2, 3, 4, 5, 6. Okay. So all are the relative prime numbers. For 8. So 1 is relative prime number. 2 is not a relative prime number to 8. 3 is relative prime. 4 is not relative prime. 5 is relatively prime. And 7 is relatively prime to 8. Okay. 1 minute. Anna. Anna. श्रीलक्ष्मी मैडम की कॉल श्रीलक्ष्मी मैडम की कॉल चाहिए. Mm. So in this way we can find the torsion function for any number. Okay. So for larger numbers we have some shortcuts to find the Euler's torsion function. Okay. So we will discuss now. चाहिए ना वो. Okay. uh, so these are the shortcuts to find the Euler torsion function. So for prime number p, okay, if a number is a prime, then we are having p minus 1 values, p minus 1 relative prime numbers to that number. So uh, if pi of 19, so here 19 is a prime number, then the pi of n is 18. And if uh, the number is for example some 23, so 23 is a prime number, then pi of n value is 22. So p minus 1. Okay. So you observe here the prime numbers. Mm. So the prime numbers 3, we are having 3 minus 1 relative primes. For 5, 5 minus 1 relative prime numbers. For 7, 7 minus 1. For 11, 11 minus 1 relative prime numbers. For 13, 13 minus 1 relative prime numbers. For 17, 16 relative prime numbers. For 19, sorry, here 19. For 19, 18 relative prime numbers. Okay. For 29, we are having 28 relative prime numbers. So if the number is prime number, then we are having p minus 1 relative primes. Next, suppose that we have two prime numbers p and q, and p not equals to q, then we show that n is equals to pq. So this means pi of n is equals to pi of p into q. Okay. Here p and q are the prime numbers. Okay. And both are not equal. Then uh, pi of p into pi of q we can written as pi of p into pi of q. Here p is a prime number, q is a prime number. So for prime numbers, here we have p minus 1 relative prime numbers. For this q minus 1 relative prime numbers. So for example, so pi of 35. So 35 is not a prime number. Okay. 35 is not a prime number. So, but it is so is equals to, it is a multiple of prime numbers. So 5 into 7. Okay. 5 into 7, 35. So we can written as pi of 5 into, okay, pi of 5 into pi of 7. So we know that uh, pi of 5 value is 4. Why? Because p minus 1. Pi of 7 value is 6. Okay, pi of 7 value is 6. So total 24 relative prime numbers are there for pi of 35. Okay, now, and another shortcut is, if n is the form of p power e, okay, then we can we can say that pi of n is equals to p power e minus p power e minus 1. So for example, pi of 8, okay, pi of 8. So 8 we can written as in the form of 2 power 3. Okay, here 2 is a prime number, e is some positive integer. Okay, 2 power 3. Then we can written as 2 power 3 minus 2 power 3 minus 1 is equals to, so 2 power 3 means 8 minus 2 power 3 minus 1. So 3 minus 1 is 2. 2 power 2 square. Okay, that is 4. So then the result is 4. Okay, so in this way we can find the uh, totient values or number of relative primes for a number. Okay, so these are the shortcuts for finding uh, uh, relative prime numbers for a number. Okay, so you see here, for value 8 there is 4 relative prime numbers, so pi of n is 4. Okay, so this is Euler's torsion function. Now we are moving to Euler's theorem. So Euler's theorem states that for every a for every a and n are relatively prime. Okay, so here a and n are relative prime numbers. Okay, so the GCD of a and n are 1. Then a power pi of n congruent 1 mod n. Okay, so in previously Fermat's theorem, here p minus 1 is there, here p is there, but here p is prime, but here n is a number, but a is a number. So here a and n is relatively prime. Then a power pi of n congruent 1 mod n. Okay, so this is true. So for example, here a value is 3. Okay, n value is 10. So pi of 10. So pi of 10 congruent 1 of mod n, mod n. So we can return this as, what is the pi of 10 value? Tell me, what is the pi of 10 value? What is the pi of 10? Section 5 students, sorry, section 2 students, 4. Okay, so pi of n value is 4. So 3 power 4. Okay, here n value is 10. Okay, n value is 10. So 3 power 4 mod 10 mod 10 is equals to 1 mod 10. 1 mod 10. Okay, so 3 power 4 value, 3 into 3 9, 27, 81. So 81 mod 10 value 1 and 1 mod 10 value 1. So both are same. Okay, so if and only if here a and n are relatively prime, and you see here next another example, a value 2. Okay, and pi of 11, n value is 11 congruent 1 mod 11. congruent 1 mod 11. So now we can written as what is the pi of 11? What is the value of pi of 11? What is the value of pi of 11? Here 11 is the prime number. Then pi of n pi of 11 is equals to n minus 1. That is 11 minus 1. So the answer is 10. So 2 power 10 mod 11 mod 11 is equals to 1 mod 11. Okay, so 2 power 10 means 1024. So 1024 mod 11 is equals to 1. Okay, 1 mod 11 also 1. So if you perform the division, then you can get remainder is 1. Okay, so this is Euler's theorem. So same as Fermat's little theorem, some alternative theorem. Here Euler's also having some alternative theorem. Here a power pi of n plus 1 congruent a mod n. Okay, so previously here in Fermat's little theorem, a power p plus 1 congruent a mod n, but here a power pi of n plus 1 congruent a mod n. So for this a is does not require relatively prime to n. So here a is does not require relatively prime to n, but here a is relatively prime to n. Okay, so that is Euler's theorem. So for Euler's theorem, we have to find the Euler's totient function. Now, uh, next, Chinese remainder theorem. One minute. Okay. Okay. Next, Chinese remainder theorem. So it is also called as CRT. Okay. So it is used to speed up modulo computations which are used in RSA like public key cryptography. Okay. So here the CRT used to solve a set of congruent equations with one variable but different modulo. So here one variable. So x is one variable but different modulo. So here these are the different modulos. Then we get different reminders. Okay. So uh, these are relatively prime. These modulos are relatively prime. Okay. Now, so when x is divided by m1, that then we got remainder a1, and the same x is divided by some other number m2, then we got a2 as the remainder, and so on. Same x divided by some mk, then we got ak. So now we have to find the x value. Okay, so this is Chinese remainder theorem. So this is used in public key cryptography like RSA. So how to find this X value? So for that we have the algorithm. Okay. So here I am taking one example. So here the equations are x is equals to, okay, x is equals to 2 mod 3. So 2, sorry, x is equal to x congruent 2 mod 3. Okay, 2 mod 3. Next x congruent 4 mod 5. So 4 mod 5. Next x congruent 5 mod 7. So 5 mod 7. So these are in the form of these equations. Okay, here small m1, small m2, small m3 are 3, 5, 7. So these are the small m values, and small a values are 2, 4, 5. This is the x value. Okay. Now the first step is calculate common modulus m. So to calculate m, we have to perform product of all different modulos, all the given modulus. So m is equals to, this is the first step. M is equals to small m1, small m2, small m3, and so on, small mk. Okay, so up to 1 to k. So here we are having three equations. That's why m1 into m2 into m3. So that is 3 into 5 into 3 into 5 into 7. So what's the value? 3 into 5 into 7. What is the value? So the value is 105. So this is the common modulo. Now the second step is calculate m1, m2, and so on mk. So this capital M1 is calculated by capital M by small m1. So here capital M is 105 by, so small m1 value is 3. So here small m1 value is 3. Now capital M1 value 35. Like that, capital M2 is calculated by 105 by 5. So 105 by 5, 21. Next capital M3 is 105 by 7. So 15. So these are the, in this way we can calculate capital M1, M2, M3. Now calculate the multiplicative inverse of M1, M2, and so on Mk using the corresponding modulo. Okay. So corresponding modulos are M1, M2, Mk. Okay. So we have to calculate the multiplicative inverse for these M. So the formula is Mi into Mi inverse congruent 1 mod M. So for first we take M1 now. So M1 value is 35. So 35 into M1 inverse. Okay, M1 inverse congruent 1 mod So small m1 is 3. Okay. Now, so 35 mod 3 means here 35 into m1 inverse mod 3. So 35 mod 3 is 2. 35 mod 3 2. So 2 into m1 inverse congruent 1 mod 3 mod 3. Okay, so here we got 2 into m1 inverse, but we need m1 inverse. So that's why అంటే ఇక్కడ మనకి లెఫ్ట్ హ్యాండ్ సైడ్ 1 రావాలి. సో ఇక్కడ మనకి ఓన్లీ 1 ఇంటూ m1 ఇన్వర్స్ అంటే m1 ఇన్వర్స్ అవుతుంది. సో అలా వచ్చేలాగా అండ్ 3 తో డివైడ్ అయ్యేలాగా మనం ఈ ఈక్వేషన్స్ ని మల్టిప్లై చేయాలి. సో ఈ ఈక్వేషన్ ని మనం 2 తో మల్టిప్లై చేస్తే ఓకే, ఈ ఈక్వేషన్ ని మనం 2 తో మల్టిప్లై చేస్తే 2 ఇంటూ 2 4. ఓకే, 4 ఇంటూ m1 ఇన్వర్స్. Okay, 4 into m1 inverse congruent 1, sorry, congruent 1 into 2 2 mod 3 mod 3. సో ఇప్పుడు ఈక్వేషన్ ఓకే అయిందా? ఇప్పుడు ఇక్కడ ఓకే, సో 2 తో 2 సైడ్స్ మల్టిప్లై చేసాం. నెక్స్ట్ ఇక్కడ సో 4 mod 3 వాల్యూ 1. సో 1 into m1 inverse congruent 2 mod 3. సో 2 mod 3. సో మనం ఇక్కడ m1 ఇన్వర్స్ వాల్యూని 2 గా తీసుకుంటాం. ఓకే, సో ఇక్కడ ఏదైతే వాల్యూ ఉంటుందో మనం దాన్ని m1 ఇన్వర్స్ వాల్యూగా తీసుకుంటాం. ఓకే, సో ఇది m1 ఇన్వర్స్. నౌ m2 ఇన్వర్స్. సో m2 into, okay, by using this formula, so m2 into m2 inverse congruent 1 mod small m2 value is 5. Okay, so capital M2 value 21. So 21 into m2 inverse congruent 1 mod 5 mod 5. So now, so 21 mod 5 value 1. So 1 into m2 inverse. Okay, 1 into m2 inverse congruent 1 mod 5. Okay, so this is mod, this is 1. So now we get here 1. So that's why m2 inverse value 1. So here the value is 1. So you see here, see m1 inverse value 2, m2 inverse value 1. Okay, so in same way so same way m3. So m3 into m3 inverse congruent 1 mod small m3 value is 7. Now here small m3 is 15. So 15 into m3 inverse congruent 1 mod 7. Now 15 mod 7 1. Okay, so 15 mod 7 is 1. 1 into m3 inverse congruent 1 mod 7. So here we got 1. Okay, so 1 into m3 inverse is m3 inverse, so m3 inverse mod 7 is again 1. Okay, m3 inverse mod 7 is 1. So now we are having only three equations. So after calculating the multiplicative inverse of modulos, now calculate the solution. Okay, now calculate the solution to the given equations by using this formula. So to find the x value, we have to perform a1 into m1 into m inverse plus a2 into m2 into m inverse plus a3 into m3 into m inverse mod m. So here a1 value is 2 into capital M1 value is 35 into, okay, capital M inverse is 2 plus a2 value is 4. Next, capital M2 value is 21. M inverse value is 1 plus a3 value is 5. Next, mk value is, m3 value is 15. m3 inverse is 1 whole mod capital M value is 105. So we have to perform this. So 2 into 35 into 2. So that is 140 plus 4 into 21 into 1, 84 plus 5 into 15 into 1, 75 whole mod capital M. So mod capital M value is 105 mod 105. So the value is 140 plus 84 plus 75. So that is 299. So 299 mod 105. So the remainder is 210. So 89. 89 is the x value. So this is the final answer. So now you can check 89 mod 3. The remainder is 2. Okay. Here 89 mod 3. So 80 29 into 3 87. Okay. 29 into 3 87. So remainder is 2. So this statement is true. So 89 congruent for mod 5. So 17 into 5 85. The remainder is 4. So this is true. And 89 mod 7. So 14 into 7. Uh, so 12 into 7 84. The remainder is 5. So all the statements are true. So the x value is 89. Okay. Now, so in this way we can find the Chinese remainder theorem. So here there is another example. So x, sorry, here x congruent 1. By mistake here x is equal to 1 typed, but here x congruent 1 mod 2, x congruent 2 mod 3, x congruent 3 mod 5, x congruent 4 mod 7. So what's the x value? So you have to calculate by your own by using these formulas. Okay. So having any doubts? So today, in this session, we discussed prime numbers, Fermat's theorem, Euler's theorem, and then Euler's torsion function, After that, Chinese remainder theorem. So ఏమైనా డౌట్స్ ఉన్నాయండి?